Exercise 11. Develop a math model for the problem. Describe the type of math problem that has resulted. Using assistance from the TI Nspire CX CAS, solve the math problem and interpret the solution. Suppose you are in charge of promoting a product. You consider running a 30-second advertisement on TV Channel 8 for a 1-week period. Upon contacting them, you find Channel 8 has a volume discount pricing structure. Couple of tables. First one, rates for prime time, and then a second table spelling out the rates for daytime. Okay, you have an advertising budget of $5,000. The Nielsen ratings for Channel 8 state that it has an average of 85,400 viewers during prime time and 21,000 viewers during the daytime. What is the optimal advertising policy for the week? Alright, getting started. Looks like a couple of variables that we certainly want to have control over would be the number of primetime spots to run and the number of daytime spots to run. So, okay, about like so. Let x equal the number of primetime spots to run and y equal the number of daytime spots to run. Another quantity, the most important quantity, I suppose, in this problem, as far as what is the optimal advertising policy, what is it we're going to try to achieve here to consider ourselves having the optimal advertising policy, probably having the most number of views would be one way to achieve that. Okay, so here we could also have, okay, so let views equal the number of times the ad is viewed. And we are interested in maximizing this, right? Okay, now what about the domain of this function here? So let's move on to that. As far as formulating the number of times the ad is viewed, we've got these Nielsen ratings. So we've got 85,400 views during prime time and 21,000 viewers during the daytime. Okay, so to get the number of views total, we could take the product of the 85,400. Alright, now that's how many primetime viewers there are. And if we run the ad X times during prime time, that's how many views it gets for prime time. And then add to that the similar quantity for daytime views. 21,000 viewers. Run the ad daytime, y times. Okay, so there's the formulation of our key function here. And what about the domain? Okay, one thing we're subject to, and that would be physical sense. X and Y are numbers of times to be running an ad, so certainly they have to be greater than or equal to 0. And secondly, since you must either purchase a spot or not purchase a spot, they must be integers as well. Okay, let's see, other restrictions. Okay, yes, we have that budget restriction. And what was that? That was the condition that we have this $5,000 budget. So then we're forced to say that our cost has got to be less than or equal to $5,000. Now, what about this cost here? It breaks up into two things we're purchasing, right? Primetime spots and daytime spots. Okay, so the cost would then be, well, you need to have your rate of a primetime spot times X, the number of primetime spots you're running, and add to that the rate of the daytime spots times Y, the number of those you're running. And that's got to be less than or equal to 5,000. Now, the trouble with the rate of primetime spot is that it's a little complicated. It's a function of how many ads you have decided to purchase. Okay, so let's start working on a bit of a formulation there. let's give this function more of an actual name here. Here it is in words. Let's call it, let's see, for short, maybe we call it PT rate. Okay, and we can define it down here. PT underscore rate of X equals, and for this we look at our given information here. Now let's see, we're going to need to go with a piecewise defined function here. We're going to need to give this a value for when X is 0, because that is something we want to be considering in this formulation. So that's not on the rate, but you have 0 charge if you have X equals to 0. Then, reading along this primetime chart, we realize that we're looking at $350, and that occurs if X is between or equal to 1 to 7. Okay, then the charge drops down to 300 if X were to be between or equal to 8 and 21. Then it gets cheaper still if we buy even more, $250, and this is the case if the X is between or equal to 22 and 35. Alright, and then the cheapest primetime spots come about if you order 636 or more of them. That brings the price down to $225. Okay, so we have that function there. Now, there's a similar situation for the daytime rates. We could call it in a similar fashion DT rate, daytime rates. So that'll be okay. Now, having spelled out these functions here, this gives us a chance to now sort of improve our description of this budget constraint further. We can now formulate this as, okay, rate of primetime spots. So now we have PT underscore rate of X, okay, that times X plus, and now we could have the DT rate of Y times Y, and we could claim this has to be less than or equal to 5,000. Now, what we could even do further, since it might be useful, is simply define this left-hand side as being the cost function, the cost of the ads. So we could go here and say that cost, a function of X and Y, is equal to everything we see here and so finally that would allow us to write this budget constraint as being cost of X, Y less than or equal to 5,000. And we can call that the ultimate version of this constraint and label it as number 3. Okay, there we are. Now let's look at this math problem we have here before us. We are maximizing the number of views. That is a linear function. Now, as far as the subject to goes, it's, well, we have X and Y have to be integers. Okay, and the budget constraint is a bit complicated looking. So, in summary, it looks like this math model is an integer programming problem. Okay, so we make a note of that. This math model is an integer programming problem, and having decided that, it's time to think about what sort of strategy we want to work on here to get this resolved. Let's take a moment and talk about strategy. Strategy for solving this integer programming problem. Basic strategy is a pretty simple idea. We're going to evaluate the views function at each point in the domain and select the largest value. Now, this is kind of tedious, and so it'll require a computer program to do. If we write a computer program for this, we're going to need to generate the domain of the views function. In order to see what needs to be done to generate the domain, as well as to help communicate the solution of this problem to someone reading it, we should probably get ourselves a graph of the domain. Now, one thing about this domain, it involves a bunch of functions that are a bit on the complicated side. So we might do well to first define all of these functions on a calculator applications within the Nspire. So, in summary, here's what we're going to do. First, we'll define all the domain relevant functions using a calculator application. Then we'll be able to graph the domain using a graphs app. Then we'll be ready to write the computer program using the program editor. And then we can check the results and write a conclusion on a notes application. Alright, so here at the Nspire, open up a new document. And let's get a calculator application going. Alright, we want to define all the domain relevant functions. First at bat, that prime time rate function, that would be one we want to get. So to define a function, it's menu, action, define, and we gave it this name pt underscore rate of x equal to, alright, it's a piecewise function. Okay, here's a good chance to use the math template for this. So we go here to the math templates and we select the npiece piecewise function template right here. Okay, we need to decide how many pieces we need. Looking at our handwritten formulation, we need 5 lines to express this function. That's 5 pieces. So move this up to 5 and click OK. For this piecewise template, you notice that there is no word if involved in any of this. When you write a piecewise function, you generally use if to the right hand side of each of your formulations, but here it's just a comma. Alright, so for starters, 0 is the first value. Hit tab to go over to the condition, and that is the x equal to 0. Hit tab, and next value is 350. Tab, and now we have this under the conditions that x is greater than or equal to 1 and less than or equal to 7. Alright, 1. And let's go to control equals to get the inequalities palette here and choose the less than or equal to x, and then control inequalities palette less than or equals to 7. And we could tab forward. Okay, next value is 300, and I think what I can do here in order to not have to go to the inequalities tab palette so frequently is I could actually take this first one, and I think I'll just copy and paste it into the other spots here, so then I only have to do editing on numbers instead of having to put in a lot of inequality signs. Okay, so maybe about like so. And then when I come here, I realize this is supposed to go from 8 to 21. So 8, 21. Tabbing down, this one goes from 22 to 35. Last one is just x greater than or equal to 36. Then over here, this value is 250. Arrow down, 225. Okay, that's everything there. Time to hit enter. And that's done. Okay, similarly, we can define the daytime rate function. So, menu, actions, define. We abbreviated it with dt underscore rate of y. Going to make that equal another piecewise function off to the math templates, npiece piecewise function template. This one also has 5 pieces. Okay, 5 there, Click on OK and begin this one in a similar way. The value is 0. Under the conditions, tab forward, y equals 0, tabbing forward, and continuing doing this as in the primetime function. Alright, so now we get to here and enter. Great. Let's see. We need to get the cost function defined. Okay. Menu, actions, define. Now this is a function of x and y. As far as its formulation goes, some shortcuts are available to us now because it is defined in terms of the primetime rate function and the daytime rate function, which we've already defined. So now we can make use of our variables menu to get a hold of these. Right now we need primetime rate of x, so in the variables menu there's a primetime rate function. Make it the argument x, arrow forward, and now let's go with a multiply by x, and then plus. Need the daytime rate function. Okay, it's in the variables menu for us now. There it is. We want it at y, forward arrow to escape the argument there, and then multiply by y, and enter. Okay, that settles the 3 domain relevant functions. Now it looks like we're ready to go ahead and try to graph the domain of this function. So here, let's go in Control, add a page, and add a graph. In the domain of this function, really we had just these few inequalities here. The physical sense ones, well, so that was x greater than or equal to 0 and y greater than or equal to 0. Alright, so that puts us in the first quadrant or on the axes. And then x and y are integers. Okay, we can eventually get that by having a grid planted on this graph. And the most complicated constraint was that budget constraint. But now that we have formulated our functions here, that is not so bad. In fact, that is the only constraint that requires an entry line here, I suppose. So let's go ahead and consider that. Now, for having cost less than or equal to 5,000, we will need the boundary line, which is the equality case. So now we're thinking about graphing the cost of xy equaling 5,000. Well, solving for y, complicated. So we can use this other method to graph a function where you have x and y tied up in an equation. We first have to make it equal to 0, which is very simple. In other words, just have cost of xy minus 5,000 equal to 0. And then you can use the zeros feature on the Nspire. We'll do it here. We'll call off for f1 of x to be the zeros of. Now we want to have that cost function. That's now in our variables menu. There it is. Cost of x, y minus 5,000. Okay, comma, and then the variable y follows here. And enter. Okay, so supposedly it's been graphed, but we don't seem to see anything. Okay, some zooming out might be an idea here. Maybe we zoom out. Okay, we know it's here in the first quadrant somewhere, so we keep zoom. Oh, okay, starting to see it now. Alright. Okay, I'm going to put away this zoom tool, and now I'll use a zoom box so that I get the domain sort of filling most of the graph space here. So back to the menu and a zoom box. Alright, maybe up there for one corner, down here for another corner, and I suppose we could put away this tool. Alright, let's just pull a little bit of this axis down here, get that a little more into sight, and otherwise, okay, we have this. Now, the kind of information we especially need for our program, because we really intend to first start off with a rectangular array of integer coordinate points, we need this rectangular array to certainly include all the domain points. and extras, it's okay, but we have to at least make sure we have the domain points involved in this rectangular array. So the question becomes, well, how big of x and how big of y do we need? We know we're starting x at 0 and y starting at 0, but how large do they get? Okay, so for instance, we sort of need the y-intercept of this curve here, right? Or this graph. Okay, let's see. To get that, we could do a tracing. And then we can just put in 0 for x, enter, and then enter again to have it placed on there. Alright, and so now we see that we need, well, a y to go at least up to 66. Okay, need that much for sure. Now, the question is, what about the x down here? Alright, we bring this down, Okay, because this graph doesn't have any continuity here, it breaks up in pieces, we're going to have some troubles getting the x-intercept to show up as a 0 there. It doesn't seem to be working so well. Okay, so let's try something else. We can put this away. We can just do a little visualization here. Okay, so what is that point about there? Okay, well, we can go ahead and do a point on this x-axis. So first you select the object, and then how about there? Okay, escape. And what are the coordinates of this point? Okay, coordinates and equations. Okay, so here's this point 17, 0, which seems to, well, it's where is that exactly as far as the domain goes, on or off? Well, okay, visualization maybe only takes us so far. We could actually just go back to our calculator page and take a look at what goes on with the cost function when evaluated at 17, 0. Little trial and error. Okay, so go to the values variables menu here, pick off the cost function, and what happens at 17, 0? Okay, it's more than 5,000. That means x equals to 17 is not part of this domain. Alright, let's go back and come down one step. In other words, what happens at 16, 0? Would that be okay? So, coming in here, trying out the cost evaluated at 16, 0. Okay, 4,800, that's in the domain. Alright, so it looks like we need to make sure that our x's go out to 16 to surely pick up the entire domain. Okay, now, as far as sort of making this look a little nicer as a graph of the domain, we could put on the grid. Okay, now how do we do that? Let's see, going to the menu, making sure that we have the scaling at 1 apiece. Alright, so let's go to this X scaling, make it 1 apiece. The y-axis on the scaling, make it 1 apiece. Now that we've done that, we can come back here, and now we can go ahead and show the grid. Okay, kind of congested, but anyway, at least we get the idea of what we're looking at here. And then we could label our graph, or we could put a little description, since we don't really have all the shading that we would like to have in such a situation as this. So let's use some descriptive text. What you find is that if you try to do text right now, it's a little difficult because the grid's on. So you actually have to first remove your grid, hide the grid rather, and then you can go ahead and now do some texting and then put the grid on afterwards. Okay, so there we have the domain is the set of all integer coordinate points which lie on the region bounded by the axes and the boundary line of the cost inequality. And then the last thing we might do is put on the grid. Okay, maybe something like that there. Alright, well, looks like we're ready to start our program, having noticed that our rectangular array is going to have x's go from 0 to 16 and the y's go from 0 to 66 at minimum. Alright, designing the program. For starters, it would be nice if we would explain to someone reading our program what's going on, and we could go strictly to a source code for this. And if you want to insert a comment into a program, you use this copyright symbol. That's the source code for a comment, and now we can explain what we have in mind for our first module here. This first module seeks the maximum number of views. It also records a point, xy, which yields this maximum. Okay, now how to begin this in our plan. We said we are going to create the domain of the function, and the first step towards that end is to get that rectangular array of all integer coordinate points that includes the domain in it. That's how we get started. So let's describe that first in words. Okay, so we plan to generate a rectangular array of integer coordinate points. This array must include the domain of the views function. Alright, so we already have graphed that domain, and we realized that we need a rectangular array that has the x's going from 0 to 16 and the y's going from 0 to 66. So to create that, we can do that with counter loops in a program. And a counter loop command starts off with the instruction of for, and then you decide the variable, which will say x, 0 the lowest number, 16 the final number, and then you have to end that command somewhere. Alright, now that would generate x being 1, 2, 3, 4, 16, and then when x hits 17, it's tossed out of the loop. Okay, also we need y coordinates as well, and similarly for now y, 0 to 66, and end that loop there. Okay, so now inside here we would have all of the xy's, where x is going from 0 to 16, y is going from 0 to 66 available to us. A little problem here, and that's that when you use this command for and x here, this will actually define x to be a variable. When using the Nspire, you want to try to avoid defining x or y or really any single letters to be variables. So to prevent that from going on, we will cause the x and y here to be simply variables within this program only. And to do that, you can initially come up here and use the local command, and we'll have x and y just be variables for just this program. Okay, now we look all set there. Now, with this array of integer coordinate points, we now need to kind of create a filter that only passes points that are in the domain. Okay, so that's our next step. Okay, so now we want to create a filter which only passes points in the domain. Well, our rectangular array generally contains almost all domain points. The one situation we need to do is put a boundary line where that cost inequality boundary line is, and so we need to keep the xy's that only have the cost less than or equal to $5,000 passing on. Okay, so to do that, we can use a conditional if-then structure. So here, if, and now we'll make sure that the cost of x, y is less than or equal to 5,000. That's the only other restriction we need to put on to force the rectangular array points to be in the domain. Alright, so if we have this, then they go on into here, and we need to end this if statement somewhere, like here. Okay, now inside here we have xy points that are in the domain, just what we want. So what to do next? Next, we should evaluate that views function at these points and keep track of the maximum value as we go along. Okay, so we want to evaluate the views function. If a new maximum value is encountered, update. In other words, make this value the new maximum value of views. So to do this, we could use a conditional statement here also. We could say something like this: if views at x, y is greater than the current maximum, so we'll say greater than, let's keep the maximum value in a Vmax location, then we'll do some updating. This conditional if has to have its end statement with it, so we'll end it down here. And okay, so if we find our views function value to be greater than the current maximum, update. So in other words, following the then, here come the updates. We would say something like the Vmax will now be assigned to be that views value that's just been encountered. Along with it, let's keep track of the corresponding x. Okay, there go all our updates, and now we should be in pretty good shape here. Couple little problems. This won't work just the way it is now. One reason being that so far in this problem we haven't yet to define a views function for the this problem, so this right now has no meaning. We can go and define it early in the program before we get into the counter loops here. So let's do that. Define views of x, y to be, just look at our initial formulation of this, and that means we're going to have the 85,400x plus 21,000y. Okay, another problem, and that is initially there is no Vmax. So if a point comes inside here and we do a comparison, the value of the views to this Vmax, there's no Vmax. Okay, so we need to give this an initial value. Something else is done in the program prior to even getting into the counter loops. So up here we can furthermore do this. Let's give it an initial value. Vmax assigned to be -1. I like to use something nonsensical. That way if I run this program and I end up with a Vmax being -1, I know that things are not even getting into the counter loops, part of troubleshooting. Let's go on to the last thing we want to do, and that would be to write the results. Alright, so we've come out of here and it's time to state the results. For that we need to use a display command, disp, and it would be nice to make a sentence that explains what we've got here. And the first thing to do would be to use some quotations so that you can use text. And the quotation could read something like, the maximum number of views is, and then this would be the end of text, so we need to put the other quotation mark here, a comma, so that something else is displayed. That something else should be the Vmax, a variable, so no quotation marks. And okay, this is a sentence that should have, I suppose, a period at the end of a sentence, and you actually have to use quotations to get text, a single period, and the other quotation mark. Okay, so now we've recorded the maximum number of views. We would also like to know a point at which that occurred, so another result to display. Okay, so we'll have to put it like this. This maximum is achieved by purchasing, okay, end of the quotes and a comma, Xmax. That's what has our primetime spots. Primetime spots and, end of quotes, comma, Ymax, comma, and then daytime spots to complete the sentence. Something else that we might just kind of throw in here as an extra result, it's easy to get. How much did this cost? How much of the budget did we use to purchase these ads? Maybe that's interesting too. So a third display sentence. Okay, so finally, the cost of this purchase is cost of Xmax, Ymax, reported there, with the dollar symbol right here, part of the text. Okay, ready to go to the Nspire and keyboard this in. Alright, so here at the Nspire, let's open up a new page. And for putting in a program, two choices. One is open up a calculator application and do it there. However, you're working on a split screen if you do so, which you may want. However, I like to have a complete screen dedicated to the programming. So what I do is I don't select any of these applications, rather press Document again and go to Insert and Program Editor, New Program. Okay, giving this a name, I suppose we could call this Exercise 11, and I accept the defaults otherwise. Hit Enter. Okay, Programming Exercise 11 is defined, and we can go directly here to our first line, and here's where we're going to describe what's going on. So we have this comment we intend to put here. So for that, Menu, Actions, Insert Comment. There's a little copyright symbol, and it's time to kind of just keyboard away here. Okay, having finished our comment, hit Enter, and the next line. Okay, we can maybe skip a space to separate our comment from our genuine programming, and let's go ahead and define X and Y to be local variables. So Menu, defining variables local. Okay, and it's X, Y. Enter. Alright, now we plan to define the views function. For that, Menu, defining variables, define. And we record. Okay, and Enter. Now we need to initialize Vmax. Assigned to be -1. And Enter. Okay, since this now gets into the core of the program, I'll maybe hit another Enter to separate a line, kind of creating a new paragraph for these crucial commands. And the first thing is this counter loop. So Menu, Control, number 5 is 4 and 4. Notice you get provided the statements and the commas, so be aware of that. First comes the variable X, then I'm going to forward arrow to get past that first provided comma and put in 0, the first number, and forward arrow to get past that comma, and 16. Okay, it might also be of interest to look down and realize that command, when pulled off the menu the way we did it, also gets its N4 statement to go with it at the same time. Okay, and now we're ready for this second line where we need another 4. So Menu, Control, 4 and 4. This is for the Y. So Y, forward arrow, 0, first value, and 66, final value. Enter. I'm going to indent a little bit here to sort of exaggerate what is the interior of the counter loops here. And now we need an if, then, and if structure. For that it's Menu, Control, if, then, end if, number 2. Okay, here's where we need that cost function. It's in the variables menu at this point. You can get it there. And cost of X, Y, forward arrow, less than or equals to, so Control inequalities palette, less than or equal to 5,000. Okay, forward arrow beyond the then, and Enter. Okay, little indentation, and we can go on to our next conditional. Back to the menu, Control, if, then, end if. And this time it is a matter of taking the views function, which we have to keyboard in. It's not a variable as yet. After this program gets run, it will become a variable, but it's not there yet. So, okay, so as we had written, we've keyboarded that all in here. Let's go down and see if we have our corresponding end statements. We do. There's some spaces that are not really necessary, so I think I will choose to delete these. There. Delete this. Delete this. Okay, there. Now this brings us to where we want to start displaying results. For that, I will actually leave a space now, since displaying results is sort of a different situation, kind of like making a paragraph in an essay here. And now we need the display command. That's a matter of going menu, input output, display. Okay, we first start off with our quotation mark there, and you notice once you put your first quotation, the Nspire automatically puts the second quotation mark and leaves you with just a text box for which you need to keyboard away. Okay, having put all that in, looks like we are about ready to now check the syntax and store this program. One way to do that is to go Control B. Okay, a nice message in the status line there, exercise 11, stored successfully. Okay, let's execute this program and see what happens. We'll need to go to an application page. Okay, here we are. Our first page is a calculator application. I have cleared the history, that's why it's blank right now. And let's go ahead and go to the variables menu, pick up our exercise 11, and enter. Okay, got something here. The maximum number of views is, let's see, that's 1.3874 million, and this maximum is achieved by purchasing 1 primetime spots and 62 daytime spots. The cost of this purchase is $5,000. Okay, so we have this result. Let's start to check it out. Well, first order of business is this really a point in the domain? So that would be 162. Well, let's go to our domain graph, and let's see. This graph, I would like to sort of leave this intact. It's kind of a finished product right now, so let's make a copy of it to work on. We can do that by going here with Control, look at the pages of the problem overall. We can decide to copy this and paste a copy of it. Okay, now we can go to this copied page and work, leaving the intact copy of this alone. And I think what would be nice would be to take a close look at the vicinity of 162 and see what we think. So this is going to be a time to go with menu and zooming, and let's try to zoom box. Let's see, first corner maybe there, second corner maybe here. Okay, put away this tool by escaping, and now let's move this graph up here, I suppose. Alright, now the this point here, let's put it on this domain graph, see what happens. So menu, points lines, point, and we can put in its coordinates. That's going to be 1, enter, 62, enter, and escape the point on tool. Okay, so here we are, and let's get its coordinates planted right nearby. Well, you know, it looks like this point is just barely in the domain, like right on the boundary. Okay, well, that's alright. That's something we wanted to see. And now we can maybe also, besides noting it does appear to be in the domain, let's challenge this with something, another purchase that is, let's pick something in the domain nearby, like let's see, what's this point here? This one's in the domain nearby. We would get an extra prime time ad if we pick this point. To be sure about what it is, we can do this. We can go menu, points lines, point on. Okay, the way the point on tool is, first you select the object you want to put a point on and click. Alright, so it's Wait, I want to get this grid point there. See, grid point, and click there. Then you're supposed to then decide specifically where on the object you want your point. In this case, the object is a point, so it's really not much to decide here. Just click again. Now it's on there. Put away that point on tool, and let me get the coordinates of this point. Okay, so this 257, huh? Okay, let's challenge the claimed optimal result with the 257 point. That means a purchase of 2 primetime spots and 57 daytime spots. Alright, let's go back to our notes page. Oh, what we need to do here is we need a notes page because we have this conclusion written on this calculator page, which means we can't be keyboarding in text at this point. So let's take this, copy it. Let's come out to the end of our document, which is page 4, and now we'll add another page, a notes page. First, paste on this statement so far. Okay, now we're talking about checking. First, let's say what we first found, and that's that the point 162 does indeed appear to be in the domain. Okay, so for our check, firstly, the point 162 does indeed appear to be in the domain. See page 3, that's our zoomed in graph page. Next, we consider the claimed optimal by considering the domain point 257. Okay, what can we do here? We can very fundamentally try to calculate the number of views from such a purchase. So we could say here, alright, to get this number of views, let's go very fundamentally so that we're also checking the formulation and the keyboarding in of our views function. Everything is suspect right now, that's why we're checking. And for that we could go to the, we can set it by math box with a Control M. And now let's take a look at the fundamental description, formulation of this problem as it was presented. Very basic information, not even a translation. And what we have then would be that this purchase would result in, let's see, 2, that's primetime spots, so that's times the 85,400, and then a plus 57 of those daytime views. That would be 57 times 21,000. Enter. Okay, and let's make this look a little better. We'll format this by having that be an equal sign so it reads properly. Okay, so the number of views is this number here, and let's complete our sentence, which is, and what is the situation here, that claimed optimal, back up here. Okay, let's take this number, okay, it actually is less than. Alright, so it looks like that the claimed optimal is indeed correct. Let's see, anything else? Yes, actually there is. There may be another way to achieve this maximum number of views, and we have not looked into that matter yet. So let's go on to talk about that. Okay, so next we need to expand the computer program to seek additional points which also yield the maximum number of views. The result, which we'll post here after we first get it, but we're going to need to design a program and keyboard it in that does just this, seeks for additional points which yields the maximum. Okay, let's work on that now. Okay, we've returned to our designing of the program page, and the next thing we do to get the second module going is perhaps to actually describe it with a comment so that somebody reading our program can understand what we're doing as well. And for that we can use a comment statement. Again, the copyright symbol is the coding for that, and let's go ahead and write a description. Okay, so we've written here, this second module seeks additional points which also yield the maximum views. Okay, now we can start the program module itself. Alright, let's see. We'll need to first recreate the domain in order to seek such points. So our first step basically could be this. So we want to regenerate the rectangular array of integer coordinate points, x going from 0 to 16, y going 0 to 66. Okay, that means counter loops, right? Alright, so perhaps here, begin our first counter loop, and it goes for the variable x, the lowest number 0, highest number 16, and the corresponding n4 statement, about here. Alright, and then we need the y coordinates to also be generated. So interior to this, another counter loop, only this one variable y, 0 to 66, and its corresponding n4 statement there. Alright, so now we've got this nice rectangular array of these points generated. Now we need to create a filter, right? We need to create a filter which passes only points that are in the domain and have the maximum value of views and are unique. So we want to create a filter which passes only points which are in the domain, yield the maximum views, and are unique. All of this. Okay, sort of a complex filter here. Filters are created with conditional statements. So we could say here, if. Alright, now to make these points be in the domain, only one other restriction is needed, right? That is that cost function has to have a value less than or equal to 5,000. And I need a logical and here. We need the number of views to equal the maximum, so that would mean and. Okay, to make sure this is a unique point, we need to ensure that it's not the same as x max, y max, something else. Alright, that means we want to make a condition that makes it differ in at least one of the coordinates. Okay, so we could have that by a parenthetical condition here. We could require that x not equal to x max or y not equal to y max. Then, okay, and the corresponding end if statement down here. We have these points that have passed all of these conditions. What should we do with them now? It's probably best to directly state these results here. No point in storing or anything like that. We should just go ahead and state the results. We're going to report any findings. That would mean a display statement, right? Okay, so then we could have display, and we would have a little sentence. Okay, so we may display a sentence that reads, the maximum views can also be achieved by purchasing, record variable x right now, that's the number of primetime spots, and report variable y, that's the number of daytime spots. Something else we may wish to do, and another sentence might be to describe the cost associated with this purchase. So yet another display statement. May wish to display the cost of this purchase is, even a dollar symbol there, and then evaluate that cost function at xy. Okay. Something else, if we process through all this and we don't find any such points, it might be nice to even directly state that kind of result as well. So here we may also. Okay, so if no additional points are found, directly state this as well. This might make it clear that we did actually search for this situation. Okay, how to do this? We want to keep track of whether or not we ever got into this portion of the loop. Did we ever find any points that actually passed through this rather strict filter and had a result pan out here? It might be nice to put in a counter variable for this sort of thing, and let's initiate the counter way back here. We have in mind counting alternative strategy, so maybe I will call this variable alt count for short, and let's initiate it up here. We can have alt count assigned to be 0 at first. Now if something goes on and we get into this interior portion of the loop, we might go here and have alt count not kicked up a notch, so we do that by a statement that says alt count assigned to be alt count plus 1. Okay, now if we get through this whole program and nothing ever gets into this loop, when we get out of these counter loops, alt count will still equal 0. Okay, so then we can have a display of a statement only under that condition. So we can use it's actually a very simple if statement for this, because it's just one command we want to execute under this condition. So it would go like this: if alt count equals 0. Now this is not even an if-then structure, this is simply an if. So if this is true, it will execute the very next statement, and the next statement should be to display the no result statement. Okay, so we can display there are no other ways to achieve the maximum views under these conditions. And if the alt count actually becomes kicked up to 1, 2, 3, or 4, this statement never gets said because of the nature of this very simple if command here. Okay, we're ready to keyboard this into our Nspire program. Alright, so here at the Nspire, it's time to go back to our program page, which, let's see, was that page 3? No, page 4. Okay, here we are, and we last left off here. Okay, we need to get to the end of our last statement. Okay, and enter. Alright, now since we're about to start a whole second module, I like to leave another space to sort of have a different paragraph here. And now it's time to put in that command. That's a matter of going to the menu and actions and insert comment. Okay, now we can keyboard in what we have already written. Okay, so this second module seeks additional points, which also yield the max views, and maybe an extra empty space there before we start with our counter loops. Okay, as usual, menu, control, 4 and 4. Okay, we want the variable x, forward arrow past that comma, 0, forward arrow past that comma, 16, enter. Alright, another counter loop, menu, control, 4 and 4. This one, the y, forward past that comma, 0, forward past that comma, 66. Okay, let's see, maybe a little indentation here. And this will be the if, then, end if structure. That's a matter of menu, control, number 2, if, then, end if structure. And here's where we're going to record our first condition, the cost. Now we can find cost in our variables menu here, and there it is. And we want cost at x comma y, forward arrow past that parenthesis, and now we'll get a less than or equal to from the inequalities palette, and 5,000. Okay, we need a logical and, A and D. Next condition, the views function, that can be found in our variables menu right now, and there it is. And we're looking at views to be evaluated at x, y, forward arrow beyond that parenthesis. We want this to be equal to Vmax. Even Vmax is in our variables menu. Okay, and our other condition, which belongs in parentheses, and we have x not equal to, it's in the inequalities palette, And xmax is now one of our variables. Space or logical or space and y not equal to control inequalities palette not equal to, and the ymax is in our variables menu at this point. Okay, parenthesis, and now we can go forward to make sure that the then is there. There it is. Okay, enter to get to the next portion, which is, well, here's where we want to record the display statement. So DISP and a quotation mark, which generates both of them, and the text box awaits our keyboarding. Okay, so we have our two display statements there. Kind of scroll forward to confirm that they really are entirely there. Alright, and then that brings us to this next line, which, well, it's time to uptick that alternate counter. Okay, there's its uptick. Oh, actually, I think we did not ever record the initial value of it. Okay, a little oversight there. Alright, let's put that in here where it was written in our handwritten version. Okay, so here we initiated alt count to be 0. Okay. Now let's see here. This space is not really necessary, and this space not necessary. Alright, now this gets us to the end of the counter loops. Here's where we're going to talk about the making the statement if there are no points found. So maybe a little indentation here, and or actually let me go one more space. Okay, now if, okay, about like so, and then the end of the program occurs. Okay, let's see how this works out for syntax. Time to do a Control B to have the syntax checked and have it stored. Control B. Great. Exercise 11 stored successfully. Alright, let's go to our calculator page. Here we are. And let's go to our variables. Our program is still in exercise 11. And enter. Oh, look at this. We got a secondary result. Okay, so actually backing up here, the program starts off by recording the module 1 result again, which we're familiar with, but then we have this. The maximum views can also be achieved by purchasing 16 primetime spots and 1 daytime spot. The cost of this purchase is $4,925. Well, let's take this conclusion and bring it to the notes page. So the result, down a line and paste. Okay, and this is a main final conclusion, so I think I'd like to take this and also make this bold font. Okay, and the last remaining detail is to check out this very last statement here a little bit here. So let me kind of back off on the font for a moment, back to regular, and consider checking this second module result. Okay, it's this idea of 16 prime spots and 1 daytime spot that's under scrutiny right now. Let's at least see that this is in the domain, because all the other portions of the program seem to be working fine based on our module 1 check, but let's make sure this thing looks to be in the domain at least that much. For that, we could go back. Well, let's see. Our nice complete domain graph is here. I think it'd be nice to actually make a copy of this so we can make a zoomed in version as we did in checking the first result. So let's go here let's take this, copy it. Let's see, I'd like it to be not this page 3, let's make it page 4 by first selecting here and then pasting. There, that makes this a page 4, which we can now take a look at. And let's do a little zooming in here. Okay, for our first corner, okay, we're in this vicinity of the domain, maybe there, and a second corner, perhaps there. Alright, I'll put away this tool by hitting escape, and let's see, let's get that point on here. So we can go menu, points and lines, point, and I'm going to start putting some parentheses, and it was 16:1, 16, enter, 1, and enter, and enter again to make sure it stays there. Oh, okay. I'm going to put away the points tool and go here and get its coordinates on here, moving them perhaps to right there. Okay, you know what? It surely appears to be in the domain. Alright, so we have that in order, and let's go ahead then back to our conclusion page and make a note of that. That, by the way, is on page 4. So we can write here. Alright, we haven't actually been, we haven't really tested out this cost function directly yet. Let's go ahead and go back to very fundamental information in the problem statement to see what we think the cost of 16 prime time spots and 1 daytime spot is. Okay, so to review the cost function, the cost of 16 primetime spots and 1 daytime spot is, here's where I think we should go to the as a math box, so Control M. Alright, so let's see, that would be 16 times, now, all the way back to that very first chart in the question statement. I'm looking at it. It says under the rates for prime time. Okay, the number 16 falls in the 8 to 21 category. That would be 300 per spot. So that makes this is times 300. And then plus, now we have this 1 daytime spot, 1, and that would be times, looking at the daytime chart, 1 would be in that first category, 1 to 14 spots. That makes it a $125 purchase, and enter. Okay, and we get the same result as our program has produced for us, which is good to see. Let's just fix up this sentence a little bit. Let's make this an equality sign here. And the units of measure, we didn't have the dollar symbol in there, so we can do this by DOLLARS. And finally, point out what we find is this is consistent with what the computer program is producing. Okay, so this is consistent with the result of the computer program, and that would about wrap things up for us here. Last thing we might do is I'll get a computer view going of our program and our graphs here, so that I can show them to you here on a larger scale than in the calculator view that I work on throughout this video. Okay, so just a summary of what we have here. Really, most of the work is right here on this very first page we did handwritten style, and that was the modeling of the problem. We translated the real problem into a math model, and that's what we had here. After we had this, we started to go to the Nspire for some assistance, and the first thing we did was graph that domain. So here's sort of a somewhat touched up version of what we did now in the computer view, and it's not maybe the most complete graph, because it would be nicer if we were to have highlighted points at all the integer coordinates that are actually in the domain, but we have this descriptive statement here in the on the page, which helps to point out what the domain is as well. Okay, then once we had this domain, we also at some points of this question decided to check out some things, and here was a zoom in which we used to convince ourselves that that first point discovered 162 was indeed in the domain, and then we also used a zoom in to demonstrate to ourselves that the other solution point 16.1 was indeed in the domain. And then we also then have our program in its fuller form here. So first we had written the first module, which, as we said there, was used to locate the maximum number of views. And having written that, we then came up with a second module down here whose purpose was to find additional points which yield the maximum number of views. And this module succeeded in finding such a point. And in fact, the second solution turned out to actually have a cheaper cost than our original find. You may have noticed that as well, by $75. Okay, and then in our summary page, we have this. We first ran the first module just to make sure that that much was working, which is a nice idea when you're doing some computer programming. Get your individual modules in order before you go putting the whole program together. And we did that at first, and then we expanded the program with the second module, which yielded our final bold font conclusion there. And then we also included some statements about how we had checked over this to be confident that it's probably correct. Okay, really good there. That's it.